MS is an inflammatory and demyelinating disease of the central nervous system. Due to the breakdown of the blood-brain barrier, the body's own immune system attacks the myelin sheaths that act as an insulator. This causes damage of the myelin sheaths, which greatly reduces the conduction speed of the axons and the formation of demyelinating lesions, which are visible on conventional MRI scans. Accurate segmentation of lesions is required to compute important MS biomarkers, such as lesion count and lesion volume, which are frequently used to measure disease state and progression. However, MS lesions vary greatly in contrast, shape, and location, which makes the automatic segmentation challenging. The segmentation of lesions is often cast as a voxel-wise classification problem. First, a number of features are extracted on or around a particular voxel, followed by a classifier, which assigns each voxel one of the two labels, lesion or non-lesion voxel. Feature selection plays an important role for the segmentation of lesions. Simple, general features like the intensities of different modalities are sensitive to contrast variations, which may result in poor segmentation performance. On the other hand, context-rich features, which are specifically designed for the segmentation of lesions, may perform much better, but require a high amount of domain knowledge and tuning. Recently, unsupervised feature learning approaches have shown great promise for extracting a rich set of features that are tuned for a particular image domain without requiring any domain knowledge. We propose a novel feature learning approach that leverages not only a set of input images, but also corresponding lesion masks to learn a set of features that are tuned to the input domain and segmentation task. Our model is a two-layer convolutional encoder network, which takes images of different modalities as input and directly calculates the final segmentation. The first layer of the model performs feature extraction by convolving the input images with a set of convolutional filter kernels. The first layer is formalized as a function that maps input images and filter kernels to feature maps. The second layer performs the final classification. Like the first layer, each feature map is convolved with the filter kernel, and the resulting images are added together to form the final lesion probability map. The lesion probabilities are then thresholded to yield a binary lesion mask. The second layer is formalized as a function that maps feature maps and filter kernels to lesion probabilities. The performance of the encoder network depends on the filter kernels, which can be learned from a training set containing input images and corresponding segmentations. The objective of the training procedure is to minimize the dissimilarity between lesion probability masks and the ground truths, where the choice of an appropriate dissimilarity function is crucial for the training procedure. Training of a neural network is formalized as an optimization problem that can be solved by gradient descent. At the beginning, all filters are initialized with random values, and an initial guess of the probability mask is calculated for each training sample, followed by the calculation of partial derivatives of the dissimilarity measure with respect to the filter kernels. The partial derivatives of the first layer can be calculated by applying the chain rule, which is also called backpropagation in the context of neural networks. Each filter is then updated by following the negative gradient, and the procedure is repeated until convergence. We have presented a new method for the automatic segmentation of MS lesions based on convolutional encoder networks. Our approach combines feature extraction and classification in a single model, which allows for the automatic learning of features that are tuned for a given combination of image types and segmentation tasks. We have also developed a new loss function that works well for segmenting underrepresented classes, such as MS lesions. Our method does not make any assumptions specific to MS lesion segmentation, which makes it applicable to a large number of segmentation tasks.